Jam Revolution. Hello. Welcome to the IMS Game Jam. This is going to be an introductory video. My name is Mark, and I'm going to tell you how to make a hardware controller. So if you're watching this, you probably stumbled upon this itch.io page for the Game Jam. I'll drop the link down below. But we are hosting a game jam on March 19th that's going to run until March 21st, where everyone builds a hardware controller to control a game. This is going to be an introductory video, so if you've never touched hardware before, that is okay. And I'm going to walk you through the process of building your first hardware controller. So we're organizing this game jam so that everyone builds an identical hardware controller, which means at the end of the jam, all of the games will be playable across everyone's controller. However, I'm going to show you some tips about coding so that if you wanted to customize your controller, you can. I just want to preface this by saying that if you deviate from the code that I'm going to write today, it won't be compatible with the other jammers, so you might want to save a version of this code for the game jam. So let's get started. So what we're doing is on this itch site, you can click this Join Jam button, and you can sign up. As of today, this is Sunday, March 7th. We have 11 days until the game jam. So please sign up. Make sure that you have some time allocated. We have a parts list of hardware that I'm going to click on in a second, and you'll be able to get all of the things that you need in advance. And we have a Discord that you can join at this link, and if you want to, ask questions, team up with someone, you can do so on the Discord. So, what I'm going to show you how to do today is build a controller. And this controller is going to be relatively simple. It's going to involve 2 buttons and a rotary encoder. Now, a rotary encoder, if you've played old-style arcade games, this is what you'd find on Arduino or what else uses a rotary encoder? Arduino is the only one that comes to mind. It's basically a spinner, right? It can endlessly spin left and right in both directions. And so it allows you to do really interesting things, and I'll get into that in a little bit. And we're going to use this circuit board called a circuit playground. And this is a board made by the company Adafruit, who's based in New York. And this runs on the Arduino platform. And so you might be familiar with Arduino. It's open hardware, so anyone can build an Arduino board. And everyone can use the same basically software to program these boards. So what we're going to do is we're going to download the Arduino IDE. We're going to install some supporting libraries for this board in particular, and I'll show you how to do all of that. But basically at the end of the day, you'll be able to hook up everything to this board, and it will act as an input device for your game. What we're going to do today is make it act as a keyboard, so it's going to do some key presses, but there are a lot of different options for microcontrollers such as this. They can do mouse inputs, gamepad inputs, and it can also write things to the serial port if you want to do some more advanced programming. So what I'm going to do first is I'm going to just go through all of the parts that we have in this kit. And so I'm going to scroll back up to this link. And if you click on this, it will link to our Adafruit wish list. And so Everything for this game jam you can buy from Adafruit, and I will go through it all, kind of one thing at a time. All right, so let's see here. So, rather than show you these tiny pictures, I'll just show you actually what these things look like. So, you're going to need a breadboard. This is a prototyping surface for circuitry. This is a half-sized breadboard, and it costs $5. And you can get larger breadboards, though you won't need them for this workshop. But Adafruit has similar breadboards that are much bigger. This is double the size. So if you feel like hardware is a thing that you might want to get into, you can get larger breadboards. We also have the rotary encoder. And this has a knob that's attached to it. And I can spin this, and it can go, forever in both directions. This has 3 pins on one side and 2 pins on the other. We're only going to be using these 3 pins. These are going to be how we read the rotary encoder. These 2 are actually for a button that is included here. We're not going to use this button today, but potentially if you wanted to use this rotary encoder, you can. You'll notice that I bent these 2 pins at 180 degrees, and that's because when I put this on my breadboard, I want to make sure that they don't interfere with the breadboard holes. So if you have a pair of pliers or something, you can bend these out just to make your life a little bit easier. We'll put that on the side for now. We have a set of these breadboard buttons that we're going to be using. And for $6, you'll get 15 of these from Adafruit. I'm only going to use 2. These are nice because they come with these plastic button attachments. Like, this is actually what it is underneath. But these can just snap right on. And these have 4 pins. And I'll explain this in a little bit, but we're only going to be using 2 of these pins to wire up a button. A button is like 2 pieces of metal that when you press it, they connect together. When you let go, they disconnect. So it's simply like a wire that you're just touching every time you press the button. Really simple concept. We'll get into that wiring in a little bit. We also have the circuit playground. I'm going to spend some time talking about why we chose this board over others. Its ability to act as a keyboard is the #1 reason, but it's also got some RGB LEDs built in, which are really cool. It has this LiPo battery port, so you can run this whole project off of a battery. I'm going to walk through the circuit playground in a little bit, but it's a really great circuit board, and it's only $17.50. So Adafruit's a great company, and they make really great quality stuff. So this is really, really, we like this for this particular project. We also are recommending these alligator clips, which allow us to clip really easily to our circuit playground, right? So I can just attach it to any of these holes, and it's not a permanent connection, but for prototyping, it makes our lives really easy. Now, if you got alligator clips, we recommended an assortment of things. You can get regular alligator clips that have this on both sides, but we opted for these kind of hybrids that have a wire on the other side, so we can easily just plug them in to the breadboard. Now, if you have regular alligator clips, that's fine. Clip them to a wire and then plug the wire in. It doesn't matter, but I would recommend for this particular lab to also just have these regular jumper wires so that we can just plug things into our breadboard with wires. You can also, for those of you that might have some electronics around the house, solid core wire, you can cut and strip to the correct size. If you have stranded wire, It's not great for breadboarding because it's usually made up of a bunch of tiny strands of copper, and when you try to plug those into these holes, they get frayed, and it's not a fun time. So if you're cutting and stripping your own wire, make sure it's solid core wire. 22 gauge is probably the size, but I'm not going to get down that rabbit hole too far. These jumpers are great for breadboarding, and this is what we have on the wish list. The other thing you will need is a USB micro. Now, you might have a USB micro lying around the house, and it might be okay. But something I just want to say up front is that a lot of these cables only carry power and not data because they're used for charging things. We need a USB micro cable that carries data. There is one on the Adafruit wish list for $3. So if you're unsure if you can use your USB micro cable to program, just pick it up, and the one on the wish list will do that job. I will show you how we can test this. So if you wanted to try yours and see if it can detect the board, we'll go through that process. Okay, so with that, let's just put everything down for a second. I'm going to jump back to our website because I want to just cover a couple things before we start building. So first things first. When you go to purchase the Circuit Playground on Adafruit, this is the website you will go to. And you can see like this GIF is really cool. It has these LEDs here that you can address. And what I love about Adafruit is that almost every product on their page has a tutorial, and they have a really, really great educational section. So I'm going to scroll down here. It's going to tell you a little bit about the Circuit Playground. I know this text is really small. So I'm just going to kind of breeze through this. This is the classic version. I know they have a bunch of different ones. And what I'm going to do is go down. Here's a little video that kind of shows how it works. But what I really want is this link. Check out our detailed tutorial for pinouts, driver installation, Arduino IDE, and more. So I'm going to click on this. And this is going to be the best resource for this particular microcontroller. I've used this word a few times, microcontroller. And essentially, it's not quite a computer, but it is a circuit board that you are writing commands to. And so I'm using this USB port to give this board a block of code, and then it will continue to just run that code forever until I rewrite it. Which means once the code's on there, I can unplug it from my computer and plug it into, a USB block, or I can plug it into a battery, and whenever it receives power, it has that code loaded on. So it'll just run that code forever. So if you wanted this to be wireless, you could get a AAA battery pack that's linked here, or a lithium polymer battery for advanced users. And you can have it be wireless, which is really cool. Unfortunately, because the code we're writing today uses this as a keyboard, you need to plug it into a computer to get it to work. So if you are thinking of a wild way to make a wireless controller for this game jam, it will not work with this code. So just warning up front. So I'm not going to read this whole thing. You have this link. If you want to go through it, you can. I'm just going to kind of breeze through the things that are important. USB port can act like a serial port, keyboard, mouse, joystick, or a MIDI controller. This is the number one reason why we chose this. The regular Arduino boards actually don't have keyboard or HID input capabilities. And so we wanted something that was an easy intro board that can also be a keyboard. So that's why we like the Circuit Playground. It has a built-in USB, means you plug it in to program it. All you need is a micro USB cable. And we'll download the Arduino IDE in just a minute. And here's some other goodies baked in. I'm not going to touch on all of these, but 10 mini NeoPixels. These are the RGB LEDs. A motion sensor. It has a triple axis accelerometer with tap detection. It has a thermistor temperature sensor. It has a light sensor. It has a sound sensor. It has a mini speaker, so it can make little sounds. It has push buttons built in, which are really hard to press, so we're going to use our own. It has a slide switch, and it has 8 alligator clip-friendly input-output pins, which means all of these clips can be used both as inputs or outputs, and I'll show you how we assign those when we code it. All 8 of those can act as capacitive touch inputs. We're not going to cover that, but that's a really cool feature. A green on LED, so you know it's on, and a red number 13 LED for basic blinking, and a reset button. So there's a lot of things on here that if you bought a regular Arduino Uno, their base model, you don't even get most of this stuff out of the box. You wouldn't get the motion sensor, the temperature sensor, the light or the sound sensor. You wouldn't get capacitive touch. You wouldn't get a MIDI control capabilities. So for $18, which is cheaper than your Arduino Uno, you get this board that has a lot more capabilities, and it is easier to use. So if you're delving into Arduino for the first time, I would highly recommend buying this board because it just is so much more versatile. So I'm going to breeze through the next couple links here because we're not going to cover a lot of this stuff in this particular tutorial. There's 2 versions of this, and this is the difference. This tells you if you have a classic, it says classic on it, and I'm just going to verify real quick. Why, yes, we have the classic. And so if you end up with the Express for some reason, just know that there are some differences here, and your code may not run. I'm not really familiar with the Express, so I don't really know what the differences are, but that's okay. So, wow, here is where everything is. So I'm just going to kind of walk you through everything. Here's all your connection pads. We're going to talk about those. Your battery connector is down here at the bottom. We're not going to worry about that. All the NeoPixels are in a circle, just inset from the pads. Accelerometer, left button, right button. Here's all your sensors kind of in the middle. This Atmega chip, this is the brain, so that's where all this processing is happening. So since we're not using a lot of this, I think we can safely skip over it. Knowing where the micro USB connector is probably important. This is how we will program our board. You can feel free to read about all of this stuff on your own time. I'm going to go through it all, but if you want to know about all the different parts, they are outlined here. I'm going to kind of breeze through all this stuff. And I'm going to skip over to the pinouts. So, let's talk about electricity for a moment. I'm going to get really, really basic, so a lot of you might know this. But when you have a circuit, and I'm just going to go back to my camera here. Let's say I have a battery. I usually have, for every circuit, I have a plus side and a minus side to my circuit. Or I have power and ground. Now, for a 9-volt battery, if I measured voltage on my power, I would see 9 volts. If I measured it on my ground, I should see 0 volts. Every electrical circuit we build is going to need a power side and a ground side. So we need to make a full circuit in order to have a signal, right? Now, this is only here for an example. We're not actually going to use a 9-volt battery. I just wanted to kind of show you how most circuits are built. On our circuit playground, we also have power and ground. And it shows you where you can hook up power and ground. So anywhere that says GND, you could see up here in the top left, and at about 3 o'clock, and down here in the bottom left are all ground. They're all the same. I can connect to any of them. And this is going to be where my 0 volts are. Now, I'm going to need ground in my circuit because I need a reference point to 0. I need to know how far my voltage is above 0. So we can think about ground as our reference. And we will be using this in our circuit. The circuit playground has 2 different power pins. It has 3.3 volts, which you can see at 9 o'clock, and then at our upper right. This is the power that the circuit playground can provide. So like my 9-volt battery can provide 9 volts. My circuit playground can provide 3.3 volts. There's also VBAT down here. This is the direct voltage from my battery, which I'm not going to use in this lesson, so we can safely ignore this. Now, because of the way that we're wiring this, we're actually not going to use the 3.3 volt pins either in our circuit, and I'll explain why when we start wiring this up. But this will just show you where the power pins are. These are not input or output pins. These are going to be voltages always. So just so you know, if you clip to these, you're either going to get 0 volts on the ground pins, 3.3 volts on the power pins. Here are our input-output pins. There are 8 of them. Now, some of them have numbers, some of them have numbers and letters. Just to show you, like over here on the right side, I have 12, 6, 9, and 10. When we write code for this, we're going to actually address these pins by number. So if I clip something to the number 6, I'm going to use 6 in my code. That's how I know where I'm hooking things up. On the left-hand side, you see I have 0 and 1 down here on the bottom left, and I have 2 and 3 on the upper left. This also says RX and TX. These are communication pins. RX and TX are receive and transmit. So this is for serial communication. If I wanted to daisy chain circuit playgrounds together, this is a little more advanced. I could use RX and TX to receive and transmit data between 2 of these boards, or any other microcontroller. SCL and SDA. This is I2C protocol. This is clock and data. And these are protocols that are used in a lot of digital communication. We're not going to really delve into them, but I just want to show you that they exist here on this board. So if you did want to do something where you needed I2C, you could use these 2 pins to communicate. A little bit more than we need in this workshop, but just so you know, that's all here. All of these 8 pads, GPIO is general purpose input output. They can all be used as digital inputs and digital outputs for LEDs, buttons, and switches. When I say digital, I mean they can be on or off. I can receive a 1 or a 0. I can send a 1 or a 0. Luckily, in this lesson, we're only going to be working in digital, although if you wanted to do analog things, it is possible. I'm going to talk about that, but just so you know, D6, 9, 10, and 11 can be analog inputs. If you have a knob that you wanted to read in values, you could do it through these 4. D3, 6, 9, and 10 can be PWM outputs. PWM is pulse width modulation. This is a fancy phrase that means analog output. Because this is a computer, I'm not going to get a smooth output wave, but pulse width modulation means it will pulse the ones at a specific amount of time that can simulate an output. So if you wanted to fade an LED, basically you can pulse it like longer and longer until it is bright, and your eyes are tricked because it's pulsing so fast that it seems like it's fading. So that's all that pulse width modulation means. D0, 1, 2, and 3 can be hardware interrupt inputs. This is a little bit more complex, but an interrupt is essentially something that when it receives an input, it stops the rest of the code. It's like a priority input. We're not going to use that today, but it is possible. And this is just basically the same thing, but it just kind of outlines everything, each pin at a time. So it tells you what everything does. Hardware serial, I already talked about. The I2C interface, I already talked about. And then some of these are already used internally. So, the left button is also hooked up to D4. The right button is hooked up to D19. So if you wanted to read in these pins, if you wanted to use your accelerometer, you would look at pin 7, which isn't one of our 8 pins, but it does exist on here for the accelerometer. So there are all of these inputs that are hooked up to the internal sensors. We're not going to look at them today. But okay, next page. I will be doing today's lesson on a Mac. So everything I'm doing is for OS X. If you are on Windows or Linux, actually just Windows users for right now, you may need to download these drivers. So I'm not going to go through this, but if you're on this tutorial following along and you're on Windows, download the latest Adafruit Windows driver installation. This is how you will talk to the board. I'm going to skip over all this, but if you're on Windows, do this step. Don't skip it, or the board won't work. All right. Arduino. Everyone's going to need to do this step. Arduino is an open source electronics platform based on easy-to-use hardware and software. There are a lot of different Arduino boards. You've probably heard the suffix Duino stuck onto the ends of things because the circuit board is open source, so anyone can build their own Arduino. What we're going to do is we're going to download the software, and I'm going to show you how it works. If you go to arduino.cc, which I have open in another tab, you can go to software. And this is the latest Arduino IDE. And here are your download options. You have Windows 7 and newer. You have Windows 8.1 or 10, Linux, and Mac releases. So if I were to click here, if you want, you can feel free to donate. You can also just download, and it will download the zip file. And so Arduino is a pretty basic program. I'm just going to show you what it looks like. When you open Arduino for the first time, it's going to look something like this. And basically, there's a lot you can do with the Arduino code. And I'm going to talk, actually, I'm going to finish talking about the circuit playground and then we'll go back to this. But this is what it should look like when you open the software. So just verify that, and we'll pop back to this in a minute. So if you get that, you know you're good to go. If I click on the Setup and Test Arduino, here's another link to the IDE that we just downloaded, the drivers, and it shows you that we can run our Blink code. I'm actually going to walk through this with you just so we can test it together. All right, it's probably time to hop over to Arduino, so let's do it. So, okay, there's a few lines that are already written here. when we first load Arduino. I have void setup and void loop. These are functions, and the Arduino board, in this case the circuit playground, needs both of these to run properly. The setup is going to run one time when this boots, and these two dashes mean this is a comment. I can write whatever I want here. So put your setup code here to run once. So we're going to tell the Arduino what pins we're using, if they're inputs or outputs, everything like that's going to go in here. I want to make sure I have curly brackets around both, around all my code. And if I highlight one curly bracket, it will show me where its partner is. So you want to make sure that you always have, your code inside of curly brackets. The loop function is going to run repeatedly over and over again, which is what this comment says. Put your main code here to run repeatedly. So whatever I write here will run over and over again. Now, before I do anything, I'm going to go to File and Save. And unfortunately, you can't see my pop-ups. So let's see here. Let me do maybe a display capture. That might be a little easier. Because we're going to be doing some stuff in the file structure. So all right. So File, Save. And I'm going to call this IMS, let's just call it Jam Controller. Now you can see this is my Arduino folder, and I've got a bunch of other code here. So like inside of my Arduino folder, this is where my code will save to. And now I see my code was renamed here at the top, Jam Controller. Now, what I'm going to do is plug in my circuit playground. And you can see that the green light has lit up, which means that I have power. And I'm just going to check to make sure that my Arduino software is reading this. So let's see here. I'm going to go up to the top. Let me shrink this a little bit so you can see the menu options. In my Arduino, I'm going to go to Tools. And what I need to do first is I need to add my circuit playground as a board. So I'm going to go to Board. Now mine is already here, but for you, you're going to go to Boards Manager. And you're going to type in at the top, Circuit Playground. And this first AVR boards by Arduino, I should see, actually, let me scroll down a little bit. This shows me all the Arduino boards, but if I scroll down, here's all my adafruit boards. Although I guess the Circuit Playground is now in the default package, which is here. You can see it right here, Adafruit Circuit Playground. This is really cool. This means that the default Arduino package now recognizes the Circuit Playground, which is made by a different company, made by Adafruit. So if this install is visible, just click on that and you'll install this package. I can also hit update, and I'll update this to the latest version. This shouldn't take too long. And any other board that you get that is Arduino compatible should be available in the boards manager. If you're building your own circuit board and you don't want to submit it through the boards manager, you can drag it into the libraries folder as well, and you'll be able to use it. A little more complicated, and we're not going to get into that, but this will work for the circuit playground. Since this is taking a while, and I know I already have the board, I'm just going to stop this because I want to continue on with our tutorial. Now, you may have to restart your Arduino in order to get this board to show up, but the next thing I'm going to do is go back to Tools, and under Board, I should see Adafruit Circuit Playground. And you can see I have Teensy boards at the top, then I have Arduino boards, and then down here I have Adafruit boards. And this is where I find my Circuit Playground. So you might have to scroll through your boards a little bit to find it, but make sure that it says Adafruit Circuit Playground under Board. The other thing I'm going to do is I'm going to go to Port. This tells me what's plugged in on my USB. And you can see that I have a port that is recognized as the Adafruit Circuit Playground, which is great. This is the board that I have plugged in. If you don't see this, you may not be using a USB cable that carries data. This is one way to know. Also, double check that everything's plugged in. And also make sure that you finished importing the Circuit Playground as a board and that you restarted your Arduino software. If you do need to troubleshoot this, you can go to the Adafruit page that I was just on, and there is a whole lot of troubleshooting that will help you to recognize the board. Because this website is so much better at this, if you have problems, I would maybe direct you here to diagnose them. And so I'm going to do the thing that they do here, and I'm going to load up some example code. I'm going to go to File, Examples, and we're going to go to Basics and Blink. This is going to be our the code that we run to say, is this board working? And so I'm going to keep this code in the background, but I'm just going to walk you through really quickly what the Blink code does. Turns on an LED for 1 second and then off for 1 second. Pin 13 is an LED, and so I already know this is built in because I saw that in the documentation. In the setup, we're gonna say it's an output pin, and then in my loop, I'm gonna write the LED high. I'm gonna delay for 1,000 milliseconds or 1 second, and then I'm gonna write it to be low and wait for another 1 second. So up here at the top, I have a check mark, and then I have an arrow. Check mark is going to verify to make sure my code doesn't have any spelling errors. Cool. I just opened an example, so it should be good. This will write the code to my board. This also checks it. So if you only want to use the arrow, you can. Let's see what happens here. So it says uploading, and now it says done uploading. So let me just kind of go over here. And now, see that LED right next to the USB port? That's blinking. So the blink code works. I know I can program this. And so now I think we're ready to get into our code. Okay. Welcome to those who skipped the tutorial. We're now going to start writing our Arduino code. I'm going to actually close the blink code because I don't need it anymore. And we're going to start writing some code. However, before we do this, we should probably do our circuit. So what I'm going to do is I'm going to connect a button. And I'm going to flip back, and we're going to use the breadboard. And I'm going to take this button, and I'm going to plug it in so it straddles this kind of center cutout here. And I'm going to put this one kind of in the first two holes. These guys can be a little bit tricky. Make sure the legs don't bend under themselves and they actually press into the breadboard, because I want to make sure I have a good connection in here. I'm going to do this one as well. Make sure you will leave enough space. And so basically, even though these buttons have 4 pins, the 2 pins on the left are identical to the 2 pins on the right. If I hook something up to the top left, it's also connected on the top right. So what I'm going to do is I'm only going to use the left side of the breadboard. I'm going to ignore the right-hand side. But just so you know that, whatever you hook up to the top row over here is also connected to the top row over here. Same with the bottom row. But as far as buttons go, when I press this, it just connects these 2 pins together. Same here. These 2 pins are getting connected together. Now, the first thing I'm going to do is I'm going to give myself a reference to ground from my circuit playground. Now, if you've ever looked at any battery, or you've opened up a car, or you've seen jumper cables, you've seen a red cable and a black cable. Traditionally, red is our positive, black is our negative. I'm going to keep these conventions, and I'm going to use black to connect ground. I'm going to use this ground pin, the 3 o'clock ground pin, and what I'm going to do is I'm going to connect it actually to the top pin in my negative column. On the breadboard here, these holes are connected in different ways. On the left-hand side, all of these pins are connected together in this column, and that's the positive column. All the pins in this negative column are connected together. So if I want to connect anything to ground, I can use anything in this column. On the right-hand side, these are the same. These plus holes are connected together. These minus holes are connected together. However, this side of the breadboard is not connected to this side of the breadboard. So unless I actually put a wire connecting these together, I can't use this minus and this minus because they're physically not connected. In the middle of the breadboard, these are connected across horizontally. So anything I plug into this hole will be connected to the next 4 holes. And this split down the middle also divides this. So everything on this side is not connected to anything on this side. So if I want to connect something to these buttons, I can use any hole. There's 4 holes remaining. 3, because this button's a little bit bigger. But let's say I wanted to connect these to ground. I can take a black wire, and I'm going to actually connect the bottom pin to ground on both of these buttons. So you can see this is in the same row as the bottom pin of this button, and this side is connected to the ground column. I'm going to do the same thing for this blue button. Now, this means that whenever I press this button, whatever is plugged into the top will be connected to ground. So I'm going to connect those to some input pins. And I'm going to use pins 9 and 10 because they're right here, and it'll be really easy. And since I've got a green button and a blue button, I'm going to use a green clip and a blue clip. So let's use this one for 9. And this one for 10. Now, what is going on here? Basically, when I push the green button, it's telling pin 9 that it is now 0 volts. So when I'm not pressing it, it's reading nothing. When I am pressing it, it's 0 volts. Same with pin 10. I'm saying when I press this, it's connected to ground. So for digital inputs, we're dealing with ones and zeros, right? And we want to read this as either a 1 or a 0, which means that when I'm not pressing this, it should be reading as a 1. And what is cool about this board is I can program these pins to read as a 1 when I'm not pressing them. And so I'm saying, okay, it's a digital 1 or a high. When I press this, it's a digital low. Okay? High, low. High, low. This is how we're going to read the voltage from this. We don't care what the voltage is. All we care about is that it's a 1 or a 0. So, let's write some button code. So the first thing I need to do is, I'm going to do this above the setup function. I'm going to just assign some variables. And this is useful because I want to know like what my button is rather than just use 9 and 10 all the time. So I'm going to make an integer, and I'm going to say button 1, and I'm going to set it equal to 9, right? That's just the pin that I used. Oops, I realized that I don't have my code visible. All right. A semicolon at the end. This is how the Arduino software knows that I am done with this line and I'm on to the next. I'm going to do the same thing for button 2. So button 1 is 9, button 2 is 10. And this is how I know what pins they're on. Okay. The next thing I'm going to do is I'm going to jump down to my setup. And I'm going to use a built-in function called pin mode. We briefly saw this in the Blink code. This essentially is how we tell our circuit playground whether we have an input or an output. So I'm going to say pin mode, open parenthesis, button 1, comma, all caps, input, close parenthesis, semicolon. And do the same thing for button 2. Now, here's the trick. This is also something that you can only do on the circuit playground and a few other boards. Remember how I said I want this to read as a high voltage when I'm not pressing it? The way I would do that in a regular Arduino is I would attach a resistor to that pin and then connect that resistor to power. And a resistor is essentially a circuit component that provides resistance to the voltage. So it's reading a high voltage, but it's reading a weak high voltage through this resistor. When I press the button, it's directly connecting it to 0. So it's saying, I see a high, it's really weak, but when I press the low, it's seeing low through no resistance at all. Now, I can turn on an internal resistor on the circuit playground just by saying input underscore pull up. It's called a pull up resistor because it's a resistor that's pulled up to the high voltage. The opposite of this is a pull down resistor. I'm not going to get too deep into explaining this. I know this is a little bit confusing, but if you write input underscore pull up, all this means is when nothing is connected to this pin, it's going to read as a high voltage. Okay. So, now, here's what we're going to do. I'm going to start my serial port. And this is handy for debugging. And so I'm going to do this in the setup. I'm going to say serial.begin 9600. This is the baud rate. This is how fast I'm transmitting data. I'm going to use this to just look at data, but I'm not actually going to use it in the final version of the code. But this will be useful when we're troubleshooting. So now, when I go down to my loop, what I need to do here is going to create some white space. The first thing I'm going to do is I'm going to read the state of my button. So even though my button 1 and my button 2 have integers that are hard-coded to 9 and 10, I'm going to need 2 more integers. Actually, I can create these down here. I'm going to create another integer in my loop called button1 state. And this is going to be digital read button1. Be careful of your capitalization. In the R in digital read has to be capitalized, semicolon at the end. So basically, I'm creating another integer that's going to store the value of my button 1 every time I run the loop. So like 30 times a second, I'm going to say, is it a 1 or a 0? Is it a 1 or a 0? Is it a 1 or a 0? I'm going to do the same thing for my button 2. And now what I'm going to do is, just for debugging purposes, I'm going to say serial.print line. This puts a line return at the end. It'll be a lot easier. Let's just look at button 1 state. And we'll see what that looks like. I'm going to go up to the top and I'm going to write this code to my board. And let me see if I can open up this little magnifying glass in the corner, in the top right. This is my serial monitor. I have a bunch of 1s. If I press my button, it goes from 1 to 0. Now this is only hooked up to my first button, right? If I press my second button, nothing happens. But this is a good test to make sure my button works. Also notice it's spitting out data very, very fast. So we're gonna work on changing this so it's not so, we don't want to clog the serial port. Awesome, that's great. So what I'm gonna do, because I don't want this to always be printing, I'm just gonna put 2 slashes in front of this, and this will comment this line out. This means that I can look at this, eventually, but right now, I'm just gonna leave it be. Okay, so I'm reading in my button 1 and my button 2. But what I want to do now is make it press a key. And I'm going to set my button 1 to press X and my button 2 to press Z. Now, in order to do this, we're going to scroll up to the very top of this code, and we're going to add a library. I'm going to say #include keyboard.h. This is a keyboard library that lets us press keys on our keyboard, which is great. And so, the other thing I have to do is I have to initialize in my setup. I'm going to do it right below my serial begin. I'm going to say keyboard.begin. And that doesn't need a baud rate. It's just open and close parentheses. And now, what I can do is, in my loop, I can create an if statement that says, here's what I'm going to do. I'm going to put a comment here and say, button 1 equals X. And I'm just going to kind of make a break. So I know if I'm scrolling where to find my my button 1 stuff. This is a trick with Arduino to kind of divide your code up. Let's say if button 1 state equals, because we're just checking, we're not setting it equal to anything, low, which is 0, right? I could put a 0 here, but high and low are the same as 1 and 0. I'm going to say if button state is low, and then I'm going to open another curly bracket. So this gets into nesting now. Notice, if I scroll down, I have a curly bracket here. This is for my if statement. And then this bottom curly bracket is actually for my void loop. So I have to make sure that I always have a matching curly bracket for when I'm nesting my code. So let's say if button state equals low, keyboard.press X. And I'm going to put that in single quotes so it knows it's the character X. And what I'm going to do next is I'm going to say delay 1000 and then keyboard.release X. This is important because we're actually manually pressing keys with Arduino. So we have to tell it when we're pressing and when we're releasing. So right now I'm going to press this for a second and then it'll release. So let's see. Let's see what happens here. I'm going to write this code. And I'm not going to open up the serial port because I should be able to just write an X. Now, I'm getting a lot of garbage. And this is because my button is a little bit noisy, right? And so what we want to do is we want to make sure that we're only pressing X one time. And so let me delete all this garbage. So what we're going to do is we're going to track state changes. This is a little bit complicated, but if you've programmed for games, this is probably really familiar. I'm going to create a variable called previous button state. And all I want to do is say, like, okay, if my button state is low, and I'm using two ands because we're checking conditions, my previous button 1 state equals high. Now this variable doesn't exist yet, but let me just copy it, and I'm gonna throw it up here at the top. Let's also do previous button 2 state. I'm not gonna assign them to anything yet, but basically this is like what my button was in the previous frame. So what I am saying here is, okay, if my button is low and previously it was high, that means I just pressed it. Which means if I'm holding the button down, it does not care because previously it was low. It's low, it was previously low, I don't care. But if it was high and it is now previously low, I should only do this once. And what I'm going to do here is, after I press it, I'll say previous button 1 state equals low. I'm going to just stop for a second because I know that this can get a little confusing. Now, what I'm going to do also is I'm going to create another condition to do my release. So we already have our release here, so I don't think we actually need this. Let's see what happens if I run this code. For some reason, it kicked me off the port, probably because I was spamming key presses. All right. Not pressing. Why is it not pressing? Well, previous button state has to be high, and we never assigned it to anything. So what I'm going to do is go up to my setup, and I'll just say previous button 1 state equals high. And I'll do this for my button 2 as well. So now I've said, okay, on startup, we'll set these both to high. And now, let's see what happens. It's still a little bit spammy. But in order to make sure that this is going to work, what I'll do is I'll just say under this, if button 1 state is high and previous button 1 state is low, we'll do a keyboard release just in case. And I'll say previous button 1 state equals button 1 state. I know I've released twice. I've put a release up here. Get rid of that garbage. So I have a delay and I'm releasing it here, but I'm just saying that if I detect a release, if I detect going from a low to a high, I'm also going to release this. And then I'm going to say previous button 1 state equals button state. All right, so now, let's see. It's still pressing a few times. I'm going to troubleshoot that in a minute, but let's turn that off for now. And what I'm going to do is copy this whole block of code, starting with my comment. Make sure I get that last curly bracket, but not the very bottom curly bracket, because remember, this is for my loop. And I'm going to paste this below. And what I'm going to do is just edit this for button 2. So I'm going to say button 2 equals Z. I'm going to change all of these button 1s to button 2s. Change my X's to Z's. Oops. And this is 2. And this is 2. The other thing I'm going to do here is this 1,000 delay. This is kind of a lot. I'm going to make this an integer called debounce. And those of you who are maybe really big into Street Fighter or Killer Queen, you probably are familiar with debounce. It's basically an amount of milliseconds that allows the button to kind of like chatter. Because when you press a button, it will go from 1 to 0 really fast for a few milliseconds. And so what I want to do is, all the way at the top here, I'm going to add int debounce, and I'm going to set it equal to, let's start with 100 milliseconds. This might be a little long, but this means that for 100 milliseconds after the key press, I'm just going to ignore things. And I can change this later if it's too long. But if I write this code now, let's see what happens. Also, it might be bad practice to do my testing inside of Arduino, so maybe open a text editor when you're testing, because you might end up with rogue X's and Z's around. So I'm feeling good about this. With tracking previous states and debounces, you know, it feels a lot better. I'm not getting so much spamming. I could probably safely drop this to 50 if I want, and it would work fine. But I think I feel good about my buttons. So what I'm going to do now is add another comment here, and I'm going to say check rotary encoder. Now, what is a rotary encoder? I found a website here that kind of tells us how rotary encoders work using a GIF. There's 3 pins, right? I showed them to you. One of our pins is ground, and that's going to be the middle pin. I'll wire this up in a minute. My 2 pins A and B are essentially out of phase by 90 degrees, which means that as I turn this, they are connected to ground kind of one after another and then disconnected. So like if this is pin A and this is pin B, they're getting connected to ground as you turn and then disconnected, then connected, and then disconnected. And this is kind of the pulse that you get, right? So what this means is if I turn this clockwise, A gets connected first, then B, and then A gets disconnected, then B. Then A, then B, then an A, then B. If I turn it counterclockwise, it means B is connected, then A, B is disconnected, then A. B, A, B, A. So if I have a way to check which of the pins is connected first, is it A or B, I know which direction I'm going. So the way we're going to do this is we're going to first look at pin A. And we're going to say, okay, this blue wave is A, right? So I'm going to say if A is high, then I'm going to look at B. If B is low, then I know I'm going clockwise because A is connected and B is not yet connected. However, if A is high and B is also high, that means I'm going in the opposite direction because B is connected already and then A. Okay? So, this is the logic here. I'm going to check one pin, and then after that, I'm going to check the other pin. Okay? So first things first, let's wire this up because we need to know what these pins are. I'm going to take my rotary encoder, and I'm going to just care about these 3 pins. I'm going to connect them. I'm going to put a little bit of space, but I'm going to put them like down here somewhere. And again, I want to make sure they go into the breadboard. Sometimes this could be a little bit tough because the spacing is a little bit weird. So if you need to pull this out and sort of like align your pins, you should do that. This guy's getting a little bit bent. Okay, this feels good. So first things first, the middle pin is ground. So I have my ground rail already. I'm going to connect that. And then I'm going to use 2 colors that are not black, blue, or green. Doesn't really matter. I have a yellow and a red. And I'm going to connect over to, what's on this side? 6 and 12. So I'm going to plug my red and my yellow. I'll plug my red into pin 6 and my yellow into pin 12. So that's what my circuit playground looks like. They're all in a row, ground in the middle. And my rotary, I'm going to say red is pin A and yellow is pin B. Okay, let's write some code. Oh man, I think I just did that whole explanation without transitioning my scene. So let's show that again. Here's my rotary encoder. Red, black in the middle for ground, red in the top, yellow in the bottom. And I've got yellow on pin 12, red on pin 6. Sorry, I'm bad at OBS. Oh, my cat wants to go outside. Hang on. I'll let her out. All right. Okay, so back to my code. So I'm going to do kind of the same thing that I did with my buttons. I'm going to go up to the top. And if you want, you can do something like, button setup. And then under here, I could say, like, encoder setup. Comment your code. It's good practice. I'm going to make an integer called value. And I will show you why this will be useful when we start writing this code. And then I'm going to say int encoder pin A equals, what did I say? 6, or is it a 9? It's a 6. Int encoder pin B equals 12. And then I'm going to say int encoder position equals 0. And similar to how I did previous button states up here, I'm going to say int encoder pin A last equals low. And then int n equals low. So I'm going to show you what we're doing here because we need a way to see what my previous state was. Remember, I'm checking pin A first, and then I'm going to look at pin B. So what we're going to do here is we're going to use N to read my encoder pin. And actually, I'm going to get rid of this because I think this makes more sense if I do it down at the bottom. So I'm going to use N to just check my state of the encoder. I'm going to see if the last value was low and it is now currently high. I know I'm moving in some direction, right? And then once I do that, I can move on to look at pin B. And I can say, okay, if my pin B is the same, I'm moving one way. If it's different, it's the other way, okay? So what we're going to need to do first is setup. So I'm going to go to my setup, and we're going to add 2 more pin modes. Pin mode, encoder, pin A is another input, pull up, and pin mode, encoder, pin B is another pull up. Okay? So now we're going to scroll all the way down to our encoder. I'm going to add some white space just so you can see it. And I'm going to say int, let's just say n, equals digital read encoder pin A. So I'm checking my encoder pin right now, right at this moment. And like I did with my buttons, I'm going to say if my encoder pin A last is low and n is high, then we're going to check my pin B. So this if statement tells me we're moving, right? But now I'm going to add another if statement. We're getting into nesting here. So we're going to say if digital read encoder pin B is low. So let's add a comment here. I'm gonna have my brackets, but what I'm gonna do is, are we moving at all? And then, so this says we're moving. If A is low, and then we check B, and B is also low, then we know we're moving counterclockwise. Yeah. So what I'm going to do here is I'm going to say encoder position minus minus. We're moving counterclockwise. We are going to subtract from this variable. Okay? Then after this, I'm going to say else. If encoder pin is low and B is high, then moving clockwise. I just want to make sure my nesting is correct. Yep, got 3 brackets here. Encoder, position, plus, plus. And so, all I'm going to do now is either increment or decrement this variable. So I'm going to make sure I'm out of this loop, and I'm also out of, I'm also out of this loop, and I'm going to say serial.println encoder position. The other thing I have to do is I have to say above this, encoder pin A last equals n, so that I make sure that I set my previous value equal to the current value. So let's see what happens here. Nope, expected. Let's see what happened here. Oh, missing a parenthesis. Boop. If you make an error, you will get that message that will tell you exactly where your error is. So if I go back to my serial port here, let's turn my rotary encoder. So, the only thing that I messed up here is that I got clockwise and counterclockwise messed up. So I'm turning it to the right, and I'm getting minus minus. Turning it to the left, and I'm getting plus plus. So let's just fix that. That way, I know that this is actually clockwise. Counterclockwise. Swap that. So, okay, I have this variable. I don't think I'm going to really use it, but what I do want to do is use this rotary encoder to press the right arrow or the left arrow. So let's do that. If I'm moving clockwise, after this I'm going to say keyboard.press. And when I'm moving to the right, I'm going to use key underscore right underscore arrow. And I want to make sure I have a little bit of a delay here. And then I'll do a keyboard.release key, right, arrow. And then same thing down here. I'll do a keyboard dot press, key, left, arrow. And 10 milliseconds, just for stability, keyboard dot release, key, left, arrow. So basically, when I'm moving to the right, I'm pressing the right arrow key. When I'm moving to the left, I'm pressing the left arrow key. All right, so I'm not going to open up the serial port, but let's just stick this in the middle. And there we go. As I move this left and right, it's moving my cursor left and right. And then I can press these buttons and get my X and Z. So that's it. This is going to be the code that you're going to start with. I'm going to clean this up before I post it because I'm still getting a little bit of noise on my first button. But I will post this on the itch.io page so that you have reference to it. Feel free to ask questions in the Discord if there's any issues with this circuit. If you have suggestions on how it can be better, I just kind of wrote this by the seat of my pants. I'm sure there are some people out there who can write some better code than me. But I hope this was informative and that you're able to use this to make your custom hardware controller. Another thing that maybe you want to do is, you can put a little zip tie around these wires to make them nice and clean. Feel free to move these so that they feel comfortable as you play the game. You can space these buttons out if you want. But yeah, I hope that you learned something today, and I can't wait to see the games that you make. So, yeah, happy jamming.